Hi, my name is Katriana Bruce, and my project is mechanical loading of a knee implant. Okay, so some background. The knee joint is one of the most complex structures of the human body. It can withstand significant strain and injury risks in everyday exercises. Normal age-related processes and excessive weight, as well as physical inactivity, can lead to wear and tear of the joint. This project is important to us because the primary goal is to reduce the pain and improve the flexibility. One previous study found that an implant approach improved up to 50% in knee motion range. Titanium is the most commonly used implant material. Titanium and titanium alloys have great corrosion resistance, making them an inert biomaterial. A limitation for this is that there is failure of the artificial joint, and joint failure risks increase when one stresses the joint with a higher impact activity or a higher weight force. So the objective of this project is to develop an understanding of the forces on the knee implant in various exercises such as walking and jumping to find the most specific implant material to limit the stresses and strains that arise from this force. Specifically, we'll be analyzing the knee implant with two different material properties, steel and titanium, to compare the two materials, and two different loads, 600 and 9,000 newtons, to model walking and jumping of a human. Okay, so this slide is showing the finite element model details, geometry, and finite element mesh. So as you can see, by using ANSYS Workbench and the static structural feature, we put in this knee implant and put a fixed support near the base or the bottom of the assembly, and then the top is free. The governing equations used. So the mechanical properties and equations are being used from Hooke's law for stresses and strains. Boundary conditions. So the mechanical boundary conditions include a fixed bottom, where we saw in the mesh slide, where the tibia and fibula would be attached, and a vertical force in the negative y direction would be applied to model the body weight on the knee implant. The material properties. So here we are comparing the two materials we'll be using, steel and titanium. And the material properties that are essential for us in this project would be the density, modulus of elasticity, tensile yield strength, elongation at break, and the hardness. Okay, so here is showing our results from the titanium implant with 600 newtons of force. So on the left side in figure 1 is the strain contour, and we can see that the max was 1.7 times 10 to the negative 5, and that is in millimeters. And then on the right is our stress contour, showing the maximum stress of 1.7, and those units are in megapascals. Okay, so moving on to the same material implant, the titanium implant, but now with a different loading. So this is with the 9,000 Newton force to model the human jumping. So on the left we have a maximum strain of around 2.6 times 10 to the negative 4 millimeters, and a maximum stress of 25.8 megapascals. Okay, so now we're moving to the steel implant with the 9,000 Newton force to model the human jumping. So on the left we have the stress contour of 25.8 megapascals, and on the right the strain contour of 1.5 times 10 to the negative 4 millimeters as the maximum strain. And finally, the steel implant with the 600 Newton force. So on the left, the stress contour, which is 1.7 megapascals, and the strain contour on the right, which is roughly 1 times 10 to the negative 5 millimeters. Okay, results and discussion. So what trends have we observed in our results? So we will comment on this on the next slide. So our results show that for the 600 Newton force, the steel implant had a maximum stress of about 1.725 megapascals and the maximum strain of 1.02 times 10 to the negative 5 megapascals. The titanium implant had a maximum stress of 1.72 megapascals and a maximum strain of 1.75 times 10 to the negative 5 megapascals. So from this conclusion, we don't really see much of a difference between the steel and titanium knee implant from immediate strain and stress contours. So we would need to be able to observe the long-term effects of the steel and titanium materials and look at the displacement as well. And these are the references.